The next step to become more accurate in sketching these graphs is to look at factoring, which we did in the first part of this unit, so that we can find all of our intercepts. And if we graph all of our intercepts and know our end behavior, then we're going to get a fairly accurate graph of what's happening. So, in this case, this one's a really easy one to factor because, first of all, what do you notice? It's an x cubed, but do you see that you have an x value in each term? So we have a common factor. And so I can already pull out an x out of each of these. And then that leads me to something that I can factor quite easily, a parabola. So now I still have that x out in front, but this I can factor further. It's going to be x and x. To get 6, 3, and 2, I need a plus 1, so I'll make a plus 3 and a minus 2. And it's factored completely. Now, factoring it completely helps us find our x-intercepts. Algebraically, when you're finding an x-intercept, you plug in 0 for y. And the reason factoring is so powerful for solving something like this is because if I had 3 numbers in my head and I told you I was multiplying all 3 of them together and the answer would be 0, can you tell me what one of the numbers has to be? It has to be 0. There's no way you can multiply and get 0 unless one of the numbers is 0. And that's a huge idea because that's what we have here. We have 0 is equal to 3 things multiplied together. And so one of them has to be 0. Does it matter which one? It's like, oh no, 0 times 3 times 5 is 0, but 5 times 3 times 0 is something else. No, it doesn't matter which one is 0. So this one could be 0. If this one's the 0, what's x? Well, 0. What happens if this one was the 0? Then what would x be? Negative 3. And if this one was the 0, then x would be 2. And so that's why sometimes we call x-intercepts zeros. Sometimes they're called roots. So we've just found our 3 x-intercepts. So now when we go to sketch our graph, we know that our graph goes through 0, negative 3, and 2. We also know the end behavior of this graph. Since it was an x cubed graph, it acts like a line. And since the leading coefficient in front of the x cubed is a positive 1, it acts like a line with a positive slope. So now when we go to our graph, we know that our graph has to start down here and end up here, because that's what a line would do with a positive slope. Our x-intercepts give us the ability to draw a sketch of this easily and quickly. So if I'm starting down here, I have to go through this x-intercept. Oh, I want to use green. Start down here, go through this x-intercept. I have to go through this one. I have to go through this one and end up here. And we've got a fairly accurate sketch of our graph. What we don't know, okay, is I don't know how high or how low it goes through there. So if you were asked to graph this on a final exam, both the green graph and the purple graph would be given full marks based on this technique. We don't know where the maximum value is. We don't know where the minimum values are. Remember, we call this a local maximum and this one a local minimum. We don't know how far it goes down. You're going to have to study calculus next semester if you want to develop algebraic techniques to figure that out. We do have other techniques that we could use to figure those out. You have a graphing calculator. You could type this into your graphing calculator and get an idea of where it is. You also have your table of values. If we want to check, like, which point is more accurate, this green one or this purple one? If we wanted to check that, what would we have to do? We'd have to plug in 1. If you plug 1 in for x, you're going to get 1 times 4 times negative 3. You're going to get the point 1 comma negative 12. So I could use a table of values, and it appears that my purple graph is more accurate than my green one, just by plugging that value in. I also don't know for sure that that's exactly where my minimum is. It might be, but it's not guaranteed. It just, we're so used to parabolas being symmetrical that when you have a x-intercept here and x-intercept there, you would say, oh, I feel like the minimum should be right in between them, but that's not guaranteed. It could have gone through that and went way down and had a different minimum somewhere else. But right now, what we're trying to do is develop skills in graphing. Now, when we use this technique, we're going to want to find our x-intercepts. We're also going to want to find our y-intercepts as well. How do you find a y-intercept? You put x equal to 0. So algebraically, x-intercepts, y equals 0, y-intercepts, x equals 0. So you're going to plug those values in and find out what your answer is going to be. This is not a very good example for that, because what happens when I plug in x equals 0? I get 0. And it doesn't help me with my graph because I already knew that point. It doesn't add anything to my graph. So we're going to also do, or look at the one off to the side. So the one that they've provided the notes for, we're going to look at that one as well, because it's a more typical type of question. This one right here. 2x to the 4 minus x cubed minus 14x squared plus 19x minus 6. First of all, can you see that there's no common factor in here? So this is more typical because for this question, ooh, that's pretty. For this question, you're going to have to use your factor theorem and synthetic division to factor it. So if I want to find all of my x-intercepts, I'm going to need to factor fully, which is something we did on our first quiz. What does factoring fully mean? Remember, you look at this last value, which is a 6, and you think of all the factors of that 6. You don't have to list them, but then you start plugging them in. So what happens when I plug in f of 1? If I get f of 1 equals 0, this is the important thing I just figured out, that x minus 1 is a factor. Once you find one factor, use synthetic division to divide it, and then you can write your division statement. Right? Remember, our division statement is that Dairy Queen thing plus a remainder. But whenever your remainder is 0, that's gone, and you've just started to factor it. So by finding out that x minus 1 is a factor and using synthetic division, we were able to start to factor this, and we get x minus 1 times, and we still have something big. So we have to repeat this process. We now check this new one that's underlined in blue, and we say, here in the textbook they changed it and called that one p of x. So now I need to factor that, and I try 1, it doesn't work. I try negative 1, doesn't work. So you keep trying, and finally they tried 2, and so the important thing is now they find out that x minus 2 is a factor. So again, you use synthetic division with your new polynomial and break it down. And then what we have here is your original division statement. you already knew that x minus 1 was a factor from before, and now you know that x minus 2 is a factor, and you could write what's left as the 2x squared plus 5x minus 3. And you finally get to a place where all you have left is a quadratic. So we can factor that one completely, right? And we have our original one completely factored. And once it's completely factored, you can easily see the x-intercepts. If I make y equal to 0, well, then I have 4 things multiplied that equals 0. And any one of those 4 could be the one that equals 0. You don't have to show all this work. You could probably just underneath say, oh, so one x-intercept is x equals 1. Another one is x equals 2. Another one is x equals negative 3. And the final one here is x is equal to a half. We have 4 x-intercepts. What about our y-intercept? And with finding your y-intercept, it's not going to be easy to use your factored one. It's always easiest to use your original one to find your y-intercept. So here's my original one. If I plug in 0 for x, 0 minus 0 minus 0 plus 0 minus 6. So you can find out that your y-intercept is minus 6. Let's look back. Before we see the graph, let's look back at the original equation. What is the degree? Is this an even-powered function or an odd-powered function? Even. Is it positive leading coefficient or negative leading coefficient? Positive. So it's going to act like a parabola. So we know what the end behavior looks like. We know what all of the x-intercepts and y-intercepts are. So when we go to graph this, you would label your 4 x-intercepts. You would label your y-intercept. I'm not going to use this graph. I'm going to go from here so you can see it. Okay? This is what you would do. You would say, I have 4 x-intercepts. I have minus 3, so I'm going to label that one. Minus 3. I've got 1 and 2. 1 and 2. And I've got a half. Whew. It's a little tight in there. I've got a y-intercept of negative 6. Label that one. And I know that it acts like a parabola, so that means I'm going to start up here, and I'm going to end up here. So now I have to go down, okay, through, okay. And you want to make your curve as smooth as possible. Some ways to lose marks in this is if you like, oh, I got to come back through this one. Wow. Okay, you got a little bit excited going through the negative 6 and went too far to the right and you had to like swoop back. This doesn't pass the vertical line test, the purple one. Okay, so if you get a little bit sloppy in your graph and you don't pass the vertical line test anymore, you are going to lose marks. So let's get rid of that purple one. Now, what I did when I connected the dots and went through everything is probably more typical of what you're going to do. You're going to want to connect the dots. So notice how like some of you will even like make whatever your bottom dot is, you will make that your minimum. You got to kind of get a sense of what's going to make a nice smooth curve through all of these points. And so I made my minimum over here somewhere. And typically, when you go to graph these, you won't go down super far. Look at the actual graph, because the graph that they've given us is a correct graph. See how far down it goes? You don't know that. And you're not supposed to know that yet. So your more typical graph that you would do through these would probably look like this. right? And both of those, based on what we know right now, would be correct. If you really, really, really like, okay, if you like using lots of paper, okay, you could have done that and still be given full marks. Okay, if you really, you want to staple multiple papers to your final exam so that the teacher has to unroll it for 15 feet just to see it swoop down, based on this right now, you wouldn't lose a mark because we don't have an algebraic way to find that minimum yet. Again, that's why you're going to study calculus next semester. So change around your schedule, make sure you add that in. Okay?
Wait, seriously, if we did that on the exam, we wouldn't lose a mark?
There might be a level of reasonableness that you might cross. At a certain point, you might cross that ability of reasonableness. Okay? So how could you get a sense? How could you get a sense how far it goes down? Well, you could pick a value somewhere between, you could type in -2 or type in -1 and use your table of values to get a sense of how far it goes down. Right? You can use your graphing calculator and actually calculate that minimum. Does everybody know how to find maximums and minimums on their graphing calculator? Does anyone not know how to do that? Awesome. Okay, so we're going to try some of these right now, 7 and 13.